Yes. Okay, so when last we left off, we were talking about the forces that hold the nucleus together. Why does it stay together? We would expect it to fall apart. Positive charges repel. But there's this thing called the strong force, which is extremely powerful. Is that what we decided? Powerful. But it only works over extremely short distances. So how does this manifest itself in terms of isotopes? So we have what's called the island of stability. Okay. So this graph plots the number of protons versus the number of neutrons. For the smaller elements, like oxygen and carbon, it's stable with just about equal numbers of protons and neutrons. As we get higher in atomic number, we start getting more and more positivity, more and more plus charges. So what does that mean about the neutrons, the glue? What happens? Wes, yeah, we need more neutrons, even on a ratio basis, right? So we're way down at the bottom, we can get, just about a 1-to-1 ratio of protons to neutrons is stable. As we move up, more protons require a higher number of neutrons per proton. So what this is saying is the ratio of neutrons to protons has to increase as we move up number of protons. So we have all these plus charges pushing against it. We need more neutrons. We need more glue per proton. Now, we notice that this is an island. So if we are down here, below the island of stability, below stable line. This is not the stable line. This is, stable area. This is not the stable line. This is just thrown in there for you to see, this is just thrown in there for you to see where protons equals neutrons. So you can see that you require more neutrons as you go. If you're below stable, why might atoms in this area here, why might they be unstable? Talk about it at your desk for like a minute. Why might these atoms, all this area underneath, why might it be unstable? So, in theory, there's no maximum number of protons. Like, you can go on forever and ever. But on the, feasible, on a real, true feasibility level, it's not. You hit that max. Okay. So, Rudy, what'd you say? Yeah. Okay. So, not enough neutrons. I'm going to curb it as, I'm going to say it as not enough glue. Neutrons act as the glue that holds the nucleus together. So if you don't have enough glue, all of a sudden those positive charges now have nothing holding them together, so they're going to stick apart. So I like to imagine this as sort of like, you have you're holding marbles together, right? And you have glue. So the marbles are your protons. The glue is your neutrons. If you don't have enough glue and you try to hold up your marble glue piece of art, I guess, what's going to happen? Well, the marbles are going to fall off. It's not going to be stable, right? Nick, go ahead. So the question was about the strong force and whether the strong force comes just from neutrons or from the protons and neutrons. My understanding, and I'm not 100% sure about this, but my understanding is it has to do with the up-down quarks that make up protons and neutrons. So it's almost like an electrostatic attraction between the flavors, the ups and the down spins. So I think both are required, but we, like on this level of chemistry that we need to know for this class, neutrons can be thought of as the glue. Okay. Yeah, Kavish. Right, the gluons that are the glue that stick together. Yeah. Yeah. So again, like a little bit beyond where we need to be. We just need to think of the neutrons here as the glue. If we don't have enough glue, it won't stick together. Up here, we have above, that's going to look ugly. Above, stable area. Bless you. We have too many neutrons. So in this case, we have too much glue, right? So if we have too much glue in my marble and glue little piece of artwork, my art installation, if I have too much glue, I'm left with a big sticky mess that sort of falls apart, right? So above the island of stability, too many neutrons, too much glue, it'll fall apart. Below, not enough glue, the positive charges will push each other apart. But then we have like the Goldilocks zone, right? Oh, it's just right. So this whole area are the stable isotopes. Now you can look and you can see that there are many different isotopes that are stable. Say like right here, these are of the same element. You go up here, these are of the same element. These are of the same element. So it's not just that you can have two. You can have multiple stable isotopes of any given element. It's possible to have multiple stable isotopes. There are plenty of elements that don't have any stable isotopes. When you get up here, it's just too big. The strong force just can't hold it together. That's why when you talk about, Kirby had a question about a theoretical element, right? So in theory, you could have elements up to like infinite number of protons, right? But the strong force only works over that very short range. So it falls apart. If you look on the periodic table, after a certain atomic number, most of the elements are radioactive, which means they're not stable. Okay. There are certain elements, and I forget which one. There's one element. Oh, let me look. It's not polonium. It might be astatine. There's like one element that at any given time on the planet, there's 2 grams of it. Because it's a product of a radioactive decay. So something decays and becomes this, but it's so radioactive that it goes away quickly. So at any given time on Earth, there's only like 2 grams of it, which is like, this much on the entire planet. I think that kind of stuff is neat. I forget which element it is. So it might be astatine. So the question was, who discovered it? Well, so you can isolate it very quickly, or you can theorize that when you talk about the construction of the periodic table in Mendeleev, it's the next chapter of the story of chemistry, you'll see like all of these fall into a place, right? And so if there's a gap somewhere, something has to fill that gap. And so it's just a matter of finding it. And even like a lot of the larger ones, when we get up, especially to like the which probably has a name now, unquadium, like you can, they might only exist for fractions of a second, and they can be detected. Livermorium. Yeah, it's in your, oh, cool. So in your assignment books, they've named actually many of the ones that are yeah, Copernicum. Yeah, awesome. Yeah, there was a new one recently. Yeah. So we're still discovering elements, although there's not a lot of, I don't know, financial gain. It's more just to understand the way the universe works. Okay, so we went off track, but in previous years, this is one of the great things we can take out of the AP curriculum this year. We went into nuclear equations and why, like, all the nuclear reactions, and we don't have to worry about that this year, which is nice. The take home is, if you have too many neutrons, you have too much glue, it falls apart. Not enough neutrons, not enough glue, falls apart. And then we have the nice Goldilocks zone where our isotopes are stable. Okay, so things you should know. 2.3. Mass spectrometry is one experimental technique that provides us with data about the masses of atoms and molecules. One of the cool new things about the curriculum is we get into analytical methods. These are things that actual scientists use now. So mass spectrometry, I have taken classes where I've used it theoretically, but real life situations where it was used. I was working on a project at my first job. Do any of you guys carry an EpiPen? Yeah, handful of you carry an EpiPen, right? So epinephrine, you shoot yourself in the leg. It's like boom when you have an allergic reaction. So I was working on, surprise, surprise, a way. So instead of you inject it, you inhale epinephrine, so you don't have to give yourself a shot. So when we were looking at making powders out of it, which is what we did, we were looking at breakdown products, degradation products. So epinephrine in and of itself is not necessarily a particularly stable molecule. In the EpiPens you have, they have a lot of other chemicals in there that help stabilize the epinephrine. So we were looking at breakdown products. So we actually used mass spectrometry to try to prove some of the breakdown products were what we said they were. So this is actually a technique that my colleagues use to help make a product move forward. So it's something that is commonly used in industry. Yeah, what? The question was, did my project work out? The project was canceled. I still want to shut that door. The project was canceled. That also was my biggest, scariest industrial accident happened on that project. So these are powders that you're supposed to inhale, right? So I was making a big batch of this powder, and we had this device, which is like a big filter paper. And we would pulse gas on it, it would flex the filter, and the powder would fall off. So there's a nice collection jar on the bottom. So you pulse it, all the nice powder falls into the jar, I cap the jar, and I go to test it. I didn't have the jar on right, so I pulsed the air, the jar flew off, and shot basically adrenaline, that's what epinephrine is, adrenaline, into the room where I was working. And just so there's this big cloud of adrenaline in the room. So that's the worst accident I was ever a part of or / caused. And it turned out like I just didn't breathe, left the room immediately. People had to go in like hazmat suits and clean up. It was no joke. It was no joke. So the end, story time, sorry. For those of you at home, it was just story time for a little bit. So no, the project did not end up moving forward. Although reasons to keep a good lab notebook, that happened 12 years ago. I was working on that project. Right before I started working at North, another one of the projects I was working on at the same time, a patent got filed, finally. And I had to go back and give my old lab notebooks that I had used like 12 years ago as part of like a legal proceeding to get the patent filed. So if I hadn't done like very meticulous notes, the patent might not have passed. So it's important to keep good notes. All right. You never know when you're going to need them. Yeah. Right. So part of the problem, the question was, how are you supposed to inhale epinephrine if you go into anaphylactic shock? In anaphylactic shock, your throat closes, you break out in enormous hives. It's terrifying. So how are you supposed to inhale it? The theory was that if you say you're allergic to bees and you get stung by a bee, you might be hesitant to give yourself a shot. So it takes like a minute or two for that anaphylaxis to hit, right? It doesn't happen like that, although it feels like it happens like that. It happens pretty quickly, but not immediate. So the thought was, oh, you get stung by a bee. All right, I'll quickly take this, and hopefully I'll be okay. But you're right. you're too far along in the shock, you inhale it, you can't inhale it, you're like, ooh, you know, so it was not necessarily a well thought out business model, although I had nothing to do with the business model, I was just on the tech side, right? So, okay, all this is a long way away from mass spectrometry. So in mass, we shorten things in science. We call it mass spec. You know, this whole mass spectrometry, a lot of times we'll just say mass spec. So you have a gas sample, and you have a current that turns that gas into an ion. So ions have charge, right? So you accelerate those ions towards a slit, like the ones we saw that you didn't see, the ones that you will see in the video about light. So you accelerate these charged particles towards a slit, then it goes through a magnetic field, and the heavier ones don't get deflected as much as the lighter ones, right? So they have the same charge. The heavier ones don't get deflected as much. The lighter ones get deflected more easily, right? So you can separate a sample of an element or a molecule or whatever you're looking at by the individual isotopes, okay? So how we use this for epinephrine. Carbon has multiple different isotopes, 12, 13, 14 is unstable, but only over long periods of time. So knowing how many carbons, how many hydrogens, how many nitrogens, we could send it through here and see what came out. What was the atomic weight of what came out? Yeah, Rudy. Yeah, you run a current through it. A good, so like a sodium lamp, you're ionizing. There are other good examples of ionizing gases, but you can ionize things just by passing a current through. Okay, so this is schematically how it looks. What does the data look like? So these are examples, and I don't think this example is in your notes. You only have one very simple example in your notes. So the chemical formula of this molecule is C1, 2, 3, 4, 5, 6, C6, H1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, H14. Anybody know what this is called? You don't have to know. I would not expect you to know at all. Oh, darn it. It's written on the board. You didn't have to tell me that. I would have been really impressed if you had remembered that it was hexane somehow. So yeah, this is hexane. So what happens is you pass hexane through the mass spec. You notice you get a bunch of different peaks. So when you take a big molecule, hexane's not a big molecule, but it's a multi-atom substance. What will happen is when you ionize it, you can split some of the bonds. So not only do you get information about the entire molecule itself, which has an atomic weight of 86, you get information about the individual pieces of the molecule. So at 15, it means you chopped off this group here. At 29, you have this group here. At 43, you have this group here. 57, and then 71. So what we would do when I was working for this company is you would look at this pattern, and not only could you check the atomic mass of your entire molecule, you could see what individual pieces it comprised. So when you get to organic chemistry, you'll see these molecules have different side groups, and you can break those side groups off doing this and determine what their mass is. What you guys need to know, this is just like cool stuff you'll see down the road. What you guys need to know are for individual elements. So if you passed iron and ionized it and passed it through a mass spec, you would see these individual patterns. And I think this is actually the one you guys have on your sheet. What you could expect to be tested on this is, can you look at a mass spec of a single element and determine what that element is? How might you possibly do that? Well, you look. You know, you have an isotope at 54. You have a lot more of that isotope at 56. You have a little bit at 57 and a little bit at 58. So you know the average mass of this element has to be somewhere around 56. So you take that, you go to your handy dandy periodic table, you look, oh, iron, the average atomic mass is 55.845. That's very close to 56. Manganese is 54.9, that's probably a little low. Cobalt is almost 59, that's too high. So just by looking at the pattern here and saying, okay, this is the most abundant, so it's probably close to 56. I have a little more at 54 than I do at 57 and 58. It's probably a little under 56. You can figure out what element you have. Yes, why does it say 100%? This should not say 100%. That should not say 100%. That's an error. Yeah, Nick. Yeah. So the question was, if you had a closer distribution where you had, say you had, oh, I can't, okay. I was going to insert a blank slide. Let's do it up here. So you have like X, Y, and Z, and you know this is 30, 60, and 10, something like that. So it's a little harder. You might be able, just from looking at what X and Y are, determine, okay, it's going to be a little bit less than Y. So from that, you can maybe look at your periodic table and determine what element it is. It gets, I mean, I took an entire course last summer on analyzing mass spec data and another type of data that we're going to talk about tomorrow. So it gets really complicated. You guys only need the very simple. If I take a single element, I ionize it, I deflect it in a magnetic field, I get this pattern of different isotopes. How can you determine what element it is? Okay. I know we went like, this was not a straight line from point A to point B. Lots of little curves. But, so, I mean, this is cool that you get like a taste of this before you get to college, and if you take like organic chemistry. Like if you want to be a doctor, you want to be a chemist, you want to be a chemical engineer, go in biotechnology, any of those things, you're going to take organic chemistry. You'll do a lot of this in organic chemistry. But for now, you just need to be able to identify single elements. All right, so that is it. We are going to keep this, and I'm going to stop